Welcome back. In this video, I'm going to solve exercises 6 to 9 of chapter 3. Exercise 6. Let X be a compact metric space and let Xn be a sequence of X with a unique cluster point, small a. Cluster point or accumulation point in the case of a metric space means that there exists, so A is a cluster point of X and means that there exists a subsequence of Xn converging to A. When I say that it's unique, it means that if a subsequence of Xn converges, then necessarily the limit must be A. Okay. Now we know that A exists actually because X is compact. Therefore, Xn has a convergent subsequence, and therefore it must be A. Under this assumption, we have to show that the whole sequence, the original sequence, converges itself to A. And the next question, we have to give an example where if we remove the compactness assumption, the conclusion is not true. So, okay, so we reason by contradiction. This is a typical reasoning in analysis. So what does it mean that Xn does not converge to A? It means that we have to negate the condition of convergence that you know from first year and that we revisited this year. So it means that the distance between Xn and A can be made arbitrarily small from a certain rank, if n is big enough. So for every epsilon, there exists a certain rank n0, starting from which the distance between Xn and A is less than epsilon. So we have to negate this condition. And as you know from Math 1100, so the for all quantifier becomes there exists, and there exists becomes for all, and then I have to negate the last condition. So there exists an epsilon that I call epsilon 0 positive, such that for every n, we can find a bigger integer n, such that the distance between Xn and A is not less than epsilon, so it's bigger or equal than epsilon 0. Yeah. This is the negation of convergence to A. Now I don't have any choice in epsilon 0, but I have a choice in the m here. So first I take m equal 1 in this condition, then I find a bigger integer that I call n1, such that the distance between x and 1 and a is bigger or equal than epsilon 0. And now I repeat this procedure. Instead of 1, I take n1. So I take m equal n1. Therefore, I find a bigger integer n2, such that the distance between x and 2 and a is bigger or equal than epsilon. And then I repeat the procedure. Instead of n1, I take n2. Therefore, I find n3, and so on. So if I continue in this way, I construct an increasing sequence of indices, nk. So therefore, I have a subsequence x and k that satisfies this inequality by definition. Now, since x is compact, the sequence x and k has a convergent subsequence that I call x and kl. Therefore, by the assumption, x and k must converge to A. X and kl must converge to A because A is the unique cluster point or accumulation point. But this is a contradiction. Okay? Because we should have that dx and kl, the distance between dx and kl and A must be less than any positive number. So in particular, it should be less than epsilon 0 over 2 if L is large enough. But this is a contradiction. Therefore, what was wrong? My assumption was wrong. So the whole sequence converges to A. Okay. And note that I used the compactness of X to reach this contradiction. If we remove the compactness assumption, the result may fail. The conclusion may fail. Because here's an example. Take this sequence: 1, 1/2, 2, 1/3, 3, etc. Okay, so the pattern is clear. So it's easy to check here that this sequence has 0 as a unique cluster point. We already have one sequence: 1, 1/2, 1/3, 1n converge to 0. And this is the unique, actually. No subsequence of this original sequence converges to an element different from 0. But there is another sequence, 1, 2, 3, and etc., that tends to infinity. Okay, so here we have a unique cluster point, but the whole sequence does not converge to this cluster point, which is 0. Okay, and this does not contradict the previous question because this sequence does not live in a compact space. It's unbounded. Okay? Here we are taking the usual topology of R. So this concludes exercise 6. Exercise 7, a very important exercise about the distances between two sets. So here I suggest that you draw a picture just in R2, take two subsets of R2, and I will give an example later. What does the distance between A and B means? Actually, it's the smallest distance between the sets. Could be 0 actually, could be positive. Something bigger or equal than 0. By definition, DAB is the infimum over X and A of the distance between X and B that we defined in chapter 1. And DXB is by definition the infimum of Y and B of DXY. So we have two characterizations of DAB. It's the infimum of DXB or the infimum, a double infimum actually. So we can write it as infimum over XY in A times B of DXY. Okay. So in some sense, it's the smallest possible, the shortest path, if you like, the shortest distance. But it's an infimum. It need not be a minimum. Okay. So first question, we have to show that if A is compact and B is closed and A and B are disjoint, then the distance between them is strictly positive. And we have to give an example where the conclusion fails if A is not assumed to be compact. Second question, we have to show that given a set A, the set of points X whose distance to A is less than R is exactly equal to a union of balls of center A and radius R, small a and capital A. Third question, if A is compact and U is an open set containing A, then there is an epsilon positive such that the set of points whose distance to A is less than epsilon. This set actually is contained in U. So here, you can draw a picture to see what's happening. And does the result hold if A is not assumed compact? First question, I will present two methods. One involving continuous functions and the other involves sequences. We know from chapter 2 that the function of x to each x in the space x associates its distance to b is a continuous map. Actually, it's uniformly continuous and Lipschitz continuous actually, because the distance between x and so dxb minus dyb is less or equal in absolute value than dxy. Okay? So of course it's continuous, and we gave this as a fundamental example. Now, a continuous function on a compact space achieves or possesses a minimum value. Okay? So, there exists a point small a in capital A where the infimum is a minimum. Okay? This is the conclusion of the extreme value theorem. Therefore, the distance between capital A and capital B, which is the infimum by definition, is achieved at a certain point small a in capital B. This is not the case in general, okay? But here we assume that capital A is compact. Now, the fact that small a is in capital A and B are disjoint means that A does not belong to B. And since B is closed, means that A does not belong to B bar, and therefore this quantity DAB is strictly positive. And because it's 0 if and only if A belongs to B bar, or to B because B is closed. Therefore, the distance between capital A and capital B is strictly positive. Second method, we reason by contradiction. Suppose that the distance is 0. So it means that the infimum is 0. So by a property of the infimum, there exists a sequence, two sequences actually, one in A, and so a sequence, a couple of sequences, AN, BN, AN in capital A, BN in capital B, such that the distance between AN and BN tends to 0. This is a fundamental property of the infimum, okay, that we proved in chapter 1. Okay? So if capital E is a subset of R, there is a sequence, and which is bounded from below, of course, then there is a sequence in E converging to the infimum. Okay. So here we use this characterization of the E. It's a double infimum over X, Y in capital A times capital B. Okay, now, since A is compact, therefore it is sequentially compact, the sequence small a n has a subsequence A and K that converge to some point small a in capital A. But the fact that the distance between A and K and B and K tends to 0 implies that B and K converges to small a as well. Okay? This you should expect that. And you can prove that actually by using the triangle inequality. You can estimate the distance between B and K and A. Okay, so therefore B and K converges to A. Since B is closed, the limit must be in B. So therefore A is in both the intersection. So it's in both A and B, capital A and capital B. Therefore it is in the intersection. But this is a contradiction because we assume that the intersection is empty. So therefore the distance is strictly positive. Now without the assumption of compactness, the result need not hold. And here's an example. We draw a figure. Consider in R2. Always look at examples in R2 where you can see things. What is capital A? Is just the set of points above the hyperbola 1 over x. And B is just the lower half plane. Okay? Then both A and B are closed. And this is easy to prove, actually. You have several ways to prove that capital A and capital B are closed. Yet and they are disjoint, of course. And the distance between them is 0. Here's the picture. So why the distance between A and B is 0? There are several ways to see this. Intuitively, it should be clear because A and B, in some sense, meet at infinity. Okay? So they can be arbitrarily close together. You can prove that analytically, if you like, by showing that there exists a sequence in A and the sequence in B whose distance tends to 0. So you can take, for example, the sequence n1 over n. And you can take the constant sequence, for example, n0, if you like. Okay, then the distance between these two tends to 0, and therefore the distance between A and B is 0. Okay, so this is a counterexample. And this is because none of A and B is compact. They are closed but not compact because they are unbounded. Okay? So this is a counterexample. Second question is easy. Actually, you have to prove a double inequality. So let me go back to double inequality. This union is contained in this set and conversely. So I'll prove that the union is contained in this set. So we take an element in the union and we prove that it's here. So if X is in the union, what does it mean? It means that there exists a point A in capital A such that X is in the open ball of center A and radius R, and therefore the distance between X and A is less than R for some A. But the distance between X and capital A is the infimum, so it's less or equal than dx small a. So therefore it's less than R. Okay? Therefore we have this inclusion. So the union is contained in the set of X whose distance to capital A is less than R. Now conversely, we take an element X whose distance to capital A is less than R, and we prove that it is in some of these balls. So take epsilon to be, so if dx capital A is less than R, then the difference is positive, and they call the difference epsilon. Now, by a fundamental property of the infimum, as you know, dxa is the biggest lower bound. So dxa plus epsilon is not a lower bound. Therefore, there exists an element in small a that I call in capital A that I call small a, whose distance to X is less than the infimum plus epsilon, and which is R. And therefore, X belongs to the open ball of center A and radius R, and therefore it's in the union. So therefore, double inequality. Okay, now last question. We have a compact set A contained in an open set U. We have to prove that, by the way, this set can be called an epsilon neighborhood of capital A. Okay? Can draw a picture actually. What does it mean? So try to represent a set A and try to represent this neighborhood. So this is an open set containing capital A. Yes. So we have to prove that there exists epsilon positive such that this epsilon neighborhood of A is contained in U. Now, since U is open, the complement of U is closed. And since U contains A, A does not meet the complement of U. So these two sets are disjoint. So I have a compact set, capital A, and the closed set, capital B, which are disjoint. And therefore, by this first question, the distance between these two sets is strictly positive. So now I take any positive number, epsilon, should be positive, of course, less than this distance. Okay, and now it's easy to check that the epsilon neighborhood of capital A is contained in U. Okay, just write it. Test your understanding. Now, of course, the result does not hold if A is not assumed to be compact, and this is an counterexample. Take a capital A to be on the real line. Of course, you can give examples in R2 if it's easier for you. So you take capital A to be the semi-open interval 0, 1, and capital U to be the open interval minus infinity 1. So U contains A. However, this epsilon neighborhood of A is, as you may check, is just the interval, open interval minus epsilon 1 plus epsilon. And no matter how epsilon is small, this set cannot be contained in U because it contains elements strictly bigger than 1. So this is the counterexample. Okay, so this concludes exercise 7. Now, exercise 8, we asked part of this exercise in an exam some years ago, and it's an important exercise actually. We have a continuous map F between metric spaces. We say that F is proper if the inverse image under F of a compact subset of Y is a compact subset of X. So please, once again, don't confuse inverse image with direct image. The direct image under F of a compact space subset of X is of course compact, because this is just continuity. Okay? Because continuity is conserved by, compactness is conserved by continuity. But here we are talking about the inverse image. Okay? So it's not the same concept. So first question, we have to show that a proper map is a closed map, which means that it maps the direct image of a closed set as a closed set, as we saw earlier. And now, if X and Y are finite dimensional, so if X equal to Rn and Y equal Rm, equipped with the Euclidean norm or any other equivalent norm, then and F is continuous, then properness of F is equivalent to the condition that the inverse image under F of a bounded set is a bounded set. And this is equivalent to saying that f of x tends to infinity at infinity. And lastly, using this, you should be able to give examples of a proper map which is not continuous. So a proper map, give an example of a proper map and an example of a continuous map which is not proper. Okay. So properness is something extra. Okay. It's okay, so we go back to the definition. We consider a closed subset capital A of X, and you have to prove that f of A is closed. So how do I prove that? Since we are dealing with closed sets, it's better to prove that the closure of f of A is equal to f of A, and therefore we consider an element in the closure and we prove that it is in f of A, as we did so many times. What does it mean that Y is in the closure of a set? By proposition 1.8 means that there is a sequence in f of A. So necessarily this sequence is of the form f of xn, where xn is a sequence of A. So we have a sequence xn of A whose image under f converges to Y. Okay. Now, if I consider the set consisting of the range of f of xn, union the limit, we know from the lecture that this set is compact. Okay. And of course, f of xn belongs to this set, clearly. Therefore, xn belongs to the inverse image under f of k. Now, by the properness assumption, f minus 1 of k is compact. Therefore, it is sequentially compact because we are dealing with metric spaces. Therefore, xn has a subsequence xnk that converges to some limit small x. And so xnk is a sequence in capital A. Therefore, xnk is a sequence of capital A, and therefore the limit must be in A bar. But since A is closed, the limit is in A. And on the other hand, since f is continuous at x, and x and k converges to x, then, as we know, f of x and k converges to f of x. But f of x and k converges to y, because the whole sequence f of x and converges to y. And therefore, by uniqueness of limits, y equal f of x, But x is in A, so f of x is in f of A, so y is in f of A. Therefore, f of a bar is contained in f of A, and therefore we have equality and so on. Okay, so this is the first question. Now, second question, we have to show an equivalence between three conditions. So I'll prove that 1 implies 2, 2 implies 1, 2 implies 3, 3 implies 2. So 1 implies 2. It's easy, actually. I assume that f is proper, and I have to prove that the inverse image of a bounded subset of Rm is a bounded subset of Rm. Now, if B is bounded, then its closure is bounded as well, because bounded means that it's contained in a ball. So if a set is contained in a ball, the closure is contained in a ball as well. Or you can say that the diameter of B is bounded if the diameter of B is finite, but the diameter of B is the diameter of B bar. Therefore, B bar is bounded, but B bar is closed. Therefore, it's compact because we are in Rm. Okay? In Rm, we have a complete characterization of closed subsets of Rm. Compact subsets of Rm are just the closed and bounded sets. Therefore, the properness assumption implies that f-1 of B bar is compact and therefore bounded. And therefore, f-1 of B is bounded as well, because f-1 of B is contained in f-1 of B bar. So this is easy. 2 implies 1, same thing. We consider so we assume that condition 2 holds, and we prove that f is proper. So we consider a compact subset K of Rm. And as we know, it's closed and bounded. Now, continuity of f means that f-1 of K is closed. Okay, this is continuity. And the assumption of boundedness, so the condition 2 tells me that f-1 of K is bounded. So f-1 of K is both closed and bounded, and therefore it's compact because we are in Rn. Okay? Therefore, f-1 of K is compact. So 1 is equivalent to 2. Now, 2 implies 3, not so difficult. Just have to go back to the definition. So consider an arbitrary positive number m, and consider the inverse image of the closed ball of center 0 and radius m. Okay. The ball is bounded, so the inverse image under f must be bounded, because this was our assumption. And this means that, what does it mean to say that the set is bounded? It means that it's contained in a ball. Okay. Could take the ball of center 0. So this set is contained in the closed ball of center 0 and radius capital R in Rm. So so this set is contained in this set. So by contraposition, the complement of this set is contained in the complement of this set. So if x is not here, which means that if x in norm is bigger or equal than R, or strictly bigger than R, then x is not in f-1 of this closed ball. Okay, and this means that f of x is not in the closed ball of center 0 and radius m, and this means that f of x in norm is bigger than m. And this is precisely the definition of limit of f of x tends to infinity. It means that f of x in norm can be made larger than any positive number I like, if the norm of x is sufficiently big. Okay, so, and 3 implies 2. You should be able to do that, because the same idea. Okay. So you do it. Now, examples of proper maps. Now we have complete characterization of proper maps, at least in the case of a function between Rn and Rm. So any function which is continuous and tends to infinity at infinity is proper. So in particular, any polynomial is proper if you want to take from R to R. The map from Rn to R given by the exponential of the norm of x, or the exponential of norm of x squared, is proper. Why? Because it's continuous and it tends to infinity at infinity. Any homeomorphism is proper, of course, because the f-1 of k is just the direct image under f-1 of k, if f is bijective, so it's compact. However, if we consider the function e to the minus norm of x, it's continuous but not proper, because at infinity it tends to 0. Sine x is also continuous but not proper, because it doesn't tend to infinity at infinity. And so on. You can give so many examples of continuous not proper and continuous and proper. So this concludes exercise 8. Last exercise, we have to show that x squared and sine of x squared are not uniformly continuous on R, but of course they are uniformly continuous on any compact subset of R, because this is the uniform continuity theorem. Now, in the lectures, I gave you an exercise, and I hope that you solved it on your own. If F is a map between two metric spaces, then F is uniformly continuous, if and only if, for any two sequences xn and yn of x. If the distance between them tends to 0, then the distance between their images tends to 0. Okay. I hope that you prove that. So this gives us an easy criterion to prove that the function is uniformly continuous or not. So in the case of x squared, we can take, for example, xn to be n and yn to be n plus 1 over n. So here xn and yn are not convergent, but their distance tends to 0. However, if you compute the distance between their images, you will get n squared minus n plus 1 over n squared, and if you do the computation, you'll get 2 plus 1 over n squared. And this does not converge to 0. So therefore, F is not uniformly continuous. And in the case of sine x squared, I'll just give you the hint. Take xn to be radical of pi over 2 plus n pi, and yn to be the same thing, but instead of n plus 1 pi. So you should be able to check that xn minus yn tend to 0, but the distance between their images is 2, and I chose them on purpose because xn squared is just pi over 2 plus n pi, and sine of this is just minus 1 to the n, and here it's minus 1 to the n plus 1. So the distance between them is 2. So that's it. This concludes exercise 9 and the exercises of chapter 3. Thank you for attention, and in the next video I will start chapter 4 on connected spaces.